Greetings and welcome. We're talking today about conditional probability, taking a look at last night's homework on page 872. And what I first want to talk about is what is the formula to calculate conditional probability. So if I have, not P, if I have the probability of event A given that event B occurred, this is going to equal the probability of A and B occurring divided by the probability of just B occurring. All right? So that's the formula for conditional probability. All right? So let's see. I haven't even read this problem yet. Let's see what happens. So a bag contains 4 red chips and 4 blue chips. Uh-oh. Another bag contains 2 red chips and 6 blue chips. Oh, man, I hate these ones because I have to do like a tree in order to figure this out. A chip is randomly selected from one of the bags and found to be blue. What is the probability that the chip is from the first bag? What crazy sauce. So let's see. So we're finding the probability first bag given that the chip was blue. All right, is what we're talking about. So we need to figure out what's the probability of first bag and blue and find the probability of just blue, right? So it sometimes can be helpful to draw a tree here of the possible outcomes because I'm not sure. Let's see. Well, let's see what happens here. Let's see what happens. Probability first bag and blue. So in the first bag, what's the probability of getting a blue? Right, 4 out of 8. Let's see what happens here. I'm interested. And what's the probability of just blue no matter which bag they're picked from? Well, how many blue are there total? There's 10. Out of how many altogether? 16. Right, so between both bags, ignoring the fact that they're in 2 bags, 10 out of 16. So for this calculation, I'm going to do 4/8 divided by 10/16. So that's going to be 4/8 multiplied by 16/10. Or you can, if you're fancy at canceling, you might be able to do it right there. Let's see, between 8 and 16, 8 goes into 16 twice. 2 goes into 4 and 10. It looks like it's going to be 4/5. But I don't know if this accurately takes into account the tree. Let's see what happens. Let's draw a tree. Kind of a probability tree. First situation was pick a bag, right? So I could have bag 1 or bag 2. In bag 1, let's see, we've got what? Red chips and blue chips. In bag 1, I've got 1, 2, 3, 4 red chips. And I've got 4 blue chips. 1, 2, 3, 4. In bag 2, we had 6 blue chips. 1, 2, 3, 4, 5, 6. And only 2 red chips, right? 1, 2. So this is my kind of tree of all possible outcomes, right? Yeah, good enough. It's a sad-looking tree. So let's see. What was the original question again? It was, a chip is randomly selected from one of the bags and found to be blue. What is the probability that the chip is from the first bag? So let's see. If I know that the chip is blue, all right, these are my possible outcomes, right? I know that much. And of those, how many of those are from the first bag? Or the first bag, wait a minute. Yeah, right? These ones are from the first bag. So if I do purple divided by green, that's going to be what? 4 out of 4 plus 6 is 10. And I end up getting the 2/5. So it is 2/5. I wonder, did we accurately depict probability? Let's see, we said 10 out of 16. 8 and 8, yep, so there's 16. And I said 10. Yep, so that's the same. So yeah, I wonder if I am able to do this using just the formula, or if I would have had to draw this tree situation. Let's see. And then I said probability first bag and blue was 4 out of 8. I wonder, oh, no, this denominator is where I messed up right here. I said this was 4 out of 8, but that's the probability of the chip I selected being out of the first bag and blue is 4, but there was still 16 possibilities total. Okay, good. Right. Well, the success is if it's out of the first bag and blue. So that's why these ones are the what are successful. But if this is but it's still out of the total possible ways it could have occurred, I didn't take into account all of these possibilities in my denominator. So that means this would have been, oh, all sorts of interesting stuff. So this would have been 16. Oh, this is going to all cancel crazy now. Well, not terribly. So that would have been 16. This would have been 16. The two 16s would have just straight canceled. And then I would have had 2/5. Right. Okay. All right. So yeah, I'd messed up on my denominator there. Yep. Well, think about the number of successful ways it could have come out of the first bag and been blue is 4. We agree with that, right? Yeah. Okay. But I have to put this over the denominator of the total possible number of outcomes. So the number of outcomes was not just these, but those as well. So it was out of 16. I had reduced the possible number of outcomes to forcing it to being out of the first bag in any possibility, but I didn't. So in terms of defining success, it was just the first bag and blue. But in terms of total possible outcomes, I had to consider all of the outcomes. Because if I reduced the outcomes that were possible, then I messed up the probability as I just did. So, all right, good. We all learned something there. I like it. See, I think this drawing it out made a lot more sense too anyway. You could see the 4 out of 10 there. Let's see, let's look at 18. It says a 5-digit number is formed from the digits 1, 2, 3, 4, 5. Ah, excellent. What is the probability that the number ends in the digit 52 given that it is even? So let's see. Well, okay, let me slow down. So probability ends 52 given that it's even, right? So this is going to be the same as probability ends 52 and even, right? And the probability of just even, right? So, okay, so let's see if we can figure this out. So probability ends in 52, so it's a 5-digit number, but I'm saying it has to end in a 5 and a 2. So in this situation, these are forced, so the possible outcomes are 1 and 1. That's the only way that can happen. So now I'm arranging how many objects and how many locations. 3 objects, right, in 3 locations. So that's a permutation, right, of 3, 3. Or it's just going to be 3 times 2 times 1, right, is what that's going to be. So 3 times 2 times 1. Or I could call that permutation 3, 3, right? Now that's if it ends in a 52. But if it ends in a 52, it's automatically going to be even, because ending in an even number guarantees the evenness of it, right? You guys agree? So this is the outcome of ending in 52 and being even. It turns out ending in 52 is a subset of the even numbers, so I didn't have to like do any extra consideration there. So permutation 3, 3 is 3 times 2 times 1, which is 6 out of, oh, I've got to figure out what's my denominator going to be here. How many possible ways is it to arrange 5 objects, right, in 5 locations? So that's just going to be 5 times 4 times 3. Nope, that's not a 3. Times 2 times 1, or permutation 5, 5, or 5 factorial. Was that the 120, right? So 6 out of 120 is, and I'm not going to reduce this just because chances are the other one might have the same denominator. Okay, so we've got the first one. Now let's figure out the probability of even. So if it's even, well, let's see. Let's ask this: how many even numbers are there, and how many odd numbers are there? Or even digits? Let me ask. There are 2 evens and 3 odd, right? Okay. So I know that the whole number is even if what? If it ends in an even, right? Is that correct? So how many possible ways could I have this be even? Or what do I have to pick from? Right? I've got 2 to pick from. And I guess it's just one object, so permutation 2, 1 or combination 2, 1. I think those end up being the same in that case. And then I'm arranging how many other objects? Right, 4. 4 ways. Because I actually don't care where the even lands in this case. Right, it's just that I had to account for it being there. Right. So let's see, this is going to be, right, 4 times 3, bless you, times 2 times 1. Permutation 2, 1, that is 2, correct? Let's see, right? Am I crazy? I feel so off this morning. Yeah. Yeah. So that's going to be 2. So this is going to be 4 factorial is 24 times 2 is 48. Over 120, the same number of possibilities. So the overall outcome, hopefully, 6 out of 120 over 48 out of 120. So that's going to be 6 out of 48. And that reduces to what? 1/8? Yeah, 0.125. And is that the right answer? It is. Hooray! So that's the same as 12.5%. And that's actually an exact, that's not an approximation. Now, this one, I didn't necessarily have to set it up this way. Let me think of show you an alternate way. I could have actually figured this out in cases. So I could have had case 1 of 1, 2, 3, 4 ending in a 2, and then case 1 of 1, 2, 3, 4 ending in a 4. So I could have kind of considered those 2 cases, and right, there's 2 possible outcomes here. Well, I would multiply by 2. Oh. Well, okay, I think we could actually view that 2 different ways. So this would have been 4 times 3 times 2 times 1, right, in both cases. So they actually would end up being the same. This is one outcome here, one outcome there, right? So this would be 24 and 24, right? And either I could multiply it by 2 because they're 2 cases, or I could add them, right, using my OR probability logic of it was either ending in a 2 or ending in a 4, so I could add them and still get 48, right? So I would have still gotten the 48 either way. So if this whole even-odd thing had the potential of throwing you off, I just want to point out you could simplify it to being like, it either ends in a 2 or ends in a 4. Let's find the probability or the number of possible outcomes for both of those and just add them together because it's an or probability, right? Or I just multiplied by 2, which multiplying by 2 was the same as multiplying by this, which is what we ended up doing. So I just want to point out there's multiple ways to perceive that. Let's see, did I have one more problem selected? I did. Aha, excellent. All right. This says, what do we got? A card is chosen at random from a standard deck of cards, so that's fitted to. Find the probability of each given that the card is black. So this says probability Jack or 10 given that it's a black card. All right, so this is kind of my numerator situation. So I'm going to need to figure out what is the probability of Jack or 10 and black. All right, so that kind of nested logic. I just wrote blank. Black is a little bit weird. And then I also want to just compare that to the probability of just black, right? Because I'm going to divide those according to my formula. So the probability of Jack or 10, well, let's see. Well, first of all, are Jacks and 10s mutually exclusive or are they inclusive of each other? They are, wait, what was that? Exclusive. I can't have a Jack and a 10, right? So I'm just going to find the probability of Jacks and add that to the probability of 10, all right? Because they're exclusive. I don't have to subtract the overlap of Jack and 10 because that doesn't exist. So, question, how many Jacks are black? 2, all right? Actually, maybe I'll break that up this way. I don't know if this logic is always distributive, but this is the same as probability Jack and black plus the probability of 10 and black, right? I'm running out of space. There we go. So Jack and black, there are 2 out of, yeah, 2 black cards out of 52. See, I was just about to reduce my denominator there again to just being 26, but that's not what I'm describing. It's the probability of selecting a card that is Jack and a black out of the 52, so I don't want to accidentally change my denominator there. How many 10s are also black? Also 2. So this is 4 out of 52, all right? Okay. How many cards are just black cards? 26 out of 52. So I'm going to take both of those and divide them. So 4 out of 52 divided by 26 out of 52 is 4 out of 26. And that reduces, 2 goes into both of those, 2 and 13. And 2/13 is my answer. So, so that's the idea for conditional probability, where I have a given fact that has, in effect, reduced my subset, right? Reduced my sample space, kind of like with this tree, right? My number of possible outcomes I had already limited to just being the green ones here. So, thanks for watching, Internet friends. Have a great day.